everybody. Today I want to give a presentation about the three TNA projects which we conducted in the past year. It was basically all our projects were conducted in our VR cave. The first project was mainly about it was mainly a design project. It was dealing with questions of materiality and 3D modeling and in an immersive environment. The second TNA project, so the first one was conducted with Laurence Maudely from the ESAT in Rhein in France. And the second project was a joint project with the university in Budapest, and it was about application of COG-info-com channels in also in an immersive modeling scenario. And the third TNA project, which I only talk about briefly, was about using a virtual immersive environment to display certain control variables control variables in a simulation for airplane wing. First, let me tell you something about or remind you to what we have in our Virtual Reality Solution Center, because I think it's necessary to know this in order to understand what we did in the projects. So we have a 5-sided back-projected cage system with active stereo projection. We have also a holo bench, also with active stereo. We have some interaction devices which we did not use in the last TNA projects. We have each system has an optical tracking system installed. In our case, we have a 6-camera system, so 2 cameras in the rear and 4 in the front. And we have a PC-based rendering cluster with NVIDIA Quattro FX graphic cards. We also have some commercial virtual reality software available, for example, the visual decision platform from ICIDU, so that we can also run more engineering-oriented projects, which we did not do in the past 3 TNA projects. And this is important, and I have talked about it very often, and I want to make to advertise it as often as possible. Our interaction framework, it's called TUI framework. TUI stands for Tangible User Interface, and this framework allows us to embed physical objects, tools, or whatever you need into this framework, and to have easy bidirectional access, also duplex access to the object, to the data from the object, and also send data back to the object. So what is new in this framework is that you do not have a device abstraction, but an object abstraction. So I explained it very often in these seminars, and what you see here is an older version of the configuration tool. So on the left side, you have the physical devices, for example, a tracking device like an optical tracking device, or a signal device like an Arduino or a Fidget device, and then you can apply those channels or those connectors to physical objects, for example, an gripper, or it could also be a pen or some other manual tools. So this tool consists of a certain amount of input and outputs, like a button pressed or its physical position. And it can also have an LED which indicates something. So then you can easily configure from which device you receive which data and to which device you send which data. So this is entirely configured in XML, and the only thing you have to deal with in software is this object. So you get a Java or C++ object which represents these physical objects, and you don't have to care whether the position data comes from optic or magnetic tracking device and where the other information about the state of the pen come from. So we use this framework also in the project I will talk about now. And we also use these interaction devices which we developed in a past publicly funded project. These are mainly tools for modeling. So we have a stylus, basically a pen to make 3D drawings in space, line-based drawings. Then we have a two-handed modeling tool that is basically an Bezier tool where you can extrude Bezier curves in 3D space. Since recently you can also use this stylus to make 3D drawings and then extrude them in space. So it's not only line-based anymore, but you can also make extrusions with it. And the last tool we have is a snapping tool or a pliers tool, so where you can grasp objects and move them from one place to another. So these, we call them tangible user interfaces because they have a physical representation, and you do not need to issue any command or select any function on a screen, but you have a direct physical access to the functionality of the system by pressing the buttons of the tools, for example. Yeah, and then we have this this application, this immersive modeling application. What you see here is an older version of the Bezier modeling tool. So the woman has the two handles in her hands, and if she presses the buttons, this is still the wired version, if she presses the buttons, then the Bezier curve is extruded in 3D space, and you get these nicely looking shapes out of it. Here you see another example. This is a past project where students had to design lamps around the virtual bulb. So the first TNA project, our first TNA project we had in June 2012 was together with Laurence Mauderly from the École Supérieure d'Art et de Design de Reims. I'm sure I pronounced it wrong, but that's where they were from. And she brought another colleague and four design students from her university in order to conduct a TNA project which was called Sketching the Imaginary. The results of this project are about to be published in the Sketch-Based Interfaces and Modeling Symposium of the ACM in next month in Los Angeles. So what was the aim of the project? Here you see some snapshots which we made during the project. The aim of the project was to search for specific modeling approaches for the designers to use the potential of the immersive modeling environment, and this especially because even so no materiality is present. So in the virtual environment you have no materiality, but materiality is very crucial for modeling and for designing. And now was the question or the aim to investigate how designers can substitute the missing materiality or can achieve a quality in design which is similar to the quality they have when they use physical material for their design. So as I said, the setup of the study was a 2 weeks TNA project within the scope of Visionaire. The participants were basically 4 design students which were supervised by 2 tutors. One of them was Mrs. Mauderly. And the students had at least 2 years experience in product design, and altogether they stayed in the virtual reality lab in the cave for 8 hours a day. Not all at the same time. Usually 1 or 2 used the cave, and the other 2 elaborated their designs with CAD software and so on. But the cave was always occupied. And yeah, they participated voluntarily. So we split the study, or we split the project in 2 weeks. In the first project, the task was to experiment with the system and to try out the modeling tools and to get familiar with it, and also the design tutors introduced the question how to develop a vocabulary which could represent certain meanings, or let's say that they were looking for shapes or forms which could represent, for example, basic actions, as I wrote here: carrying, supporting, stretching, connecting, gathering, association, but not in a very direct way, but more in an abstract way. So they were looking for 3D shapes which could represent those actions. And the aim was to put all cultural garbage away and to try to learn the new medium from scratch, or to see what it really can do, and not to apply all the existing preconcepts, and to see what you can get from that medium, and more concentrating on the meaning rather than the effect. So this was the first week. In the second week, the aim was, or the task was, that the projects and the ideas which were identified in the first week should now be realized, and to each student was given the opportunity to elaborate further on his individual approaches, and also to always refine what they developed in the cave with Rhino tools, or with CAD tools, and the students used mainly Rhino. And also some students decided to use physical modeling aids, so they introduced some physical objects in the 3D environment, and this was also part of what they did in the second week. So what I can say is, or what we discovered, were that the students basically developed 4, I find, very interesting approaches to deal with the digital material, or to master it. And I want to go through these 4 approaches now, and I will explain what they did, and present post-study some survey afterwards. So the first approach was to use physical constraints and to use a digital source and to manually arrange certain objects. So in detail, the student developed a pendulum. So she attached the sensor of the pen to a physical pendulum and started a rotation movement, or made started the pendulum to swing. And then she used an external trigger to start and stop the creation process of the line. So when the pendulum started a rotation, she pressed start basically, and if it finished one loop, then she stopped it, so that she created 3D circles, which were physically constrained because or by the physical constraints of the physical pendulum, but she generated a digital form. So she did not use CAD functions to generate the form, but still they were very even, or they looked very good, better than if she would have drawn it by hand. But it was still not deterministic how the final shape would look like, because there was some physicality involved in the creation process. So you could say that you have physical constraints in the form finding, and what you get is kind of a digital source. So the physical movement feeds a digital source, and from this source you get some circles. And what she did then, she took all that circles, so she took it away from the digital source and placed it somewhere in the cave, and then she started to arrange all the circles to certain shapes, let's say baskets or something. And then she started, this she did in with a pliers tool, and when she finished a certain shape, which was sufficient enough or good enough, she took it to the CAD software and multiplied it. Then she took it back to the cave and drew some connection lines so that she finally got shapes like this. So these are, let's say, baskets, or what, yeah, you can determine how you want to call this object, but I would say it's there are some baskets. And where you can say that the basic form of basic structure was made by hand, or was not made by hand, but was constrained by physical constraints, and then later refined with some digital modeling aids. And so these objects appear not, do not look like computer generated, even they are computer generated. So the aim of the student to keep the craftsmanship in the process was achieved. So and we also did a 3D print of, you see it on the right side of one of those baskets, but this was only side effect or side issue. This was the first approach, which I like very much. The second approach was another one where the student used visual constraints and freehand modeling. So no physical constraints in the modeling. And what he did was that he said, okay, I need some constraints. I can't do the modeling just in 3D space. I need some constraints. But I realized that I will not find a physical constraint which can guide my movement, or which is sufficient enough. So what he did was he decided to generate a shape in a CAD tool, for example a pot, and then he took this pot to the cave and started to draw around it. So the pot, or the pre-existing visual object, served as a visual constraint. So, and he tried to punctuate this object, so not to touch it with a pen, but to draw around it. So this pot, or this visual constraining object, served as a visual guide or visual help to the designer, to make him aware where some borders for his drawings are supposed to be, and it basically was a representation which helped him to constrain his modeling movements. And the output of this modeling approach was, when he removed the original pre-existing object, he only got, what he kept was what he drew, or what he kept was his drawing, and he got those nicely looking 3D objects, which also somehow look natural or handmade, crafted, but are in fact results of his hand of his manual modeling activities. Yeah, we did not print this one, but because I'm also not sure whether you can print something like this. But this was also not the initial aim of the project, to print everything. In the third approach, the student chose a similar approach to the second one, but here she did decide to model basically containers, where in the previous approach we saw that it did not, the kind of object which serves as a visual constraint is not so important. This student decided to use something or to develop or to design containers, and she created some objects to be contained in the beginning, and created some object which can contain those objects. So the process was similar to the process before, only but the meaning was different, because containment is something which is on the semantic level very important. So, and she reversed the natural order. Usually you first create, in physicality, you first create the object which can contain something, and then you put something into that container. And here she first put something in the virtual environment which is supposed to be contained, and then she created a container around that object. And what you see here is, on the left side are two bookshelves where she created the bookshelf around some books she initially loaded into the cave and used the Bezier modeling tool to create the 3D shape. And on the right side you see some fruit bowls which were drawn around the fruits I showed on the previous slide. The last approach, the physical, was a different one. Here the student used physical constraints to make a one-to-one copy. So here in this approach we developed a copying tool, which you can see on this slide. So on the bottom you have an object to be copied and a stick which is connected to a target, to an optical target. And when you start to move the object or the little point or end of the metal stick, and on the surface of the object to be copied, then the target makes the reverse movement on the top. So you can generate some copies of the physical objects, and here you see some examples of physical objects which were copied by means of this tool. So interestingly, here we also use physical constraints. The object which is to be copied is a physical constraint. It's physically constraining the modeling process. On the other hand, it's still manual, because the user moves, the way the user moves that copy tool very much determines the final shape. So you cannot make an exact copy. There's always some variations in it. So these were the 4 approaches. And after we finished the study, we had a group discussion and asked the participant about how they experienced the new modeling possibilities. So, and the students reported that somehow their understanding of 3D modeling changed. They were very certain in the beginning that they are capable of 3D modeling with CAD tools, but they said that this experience to use a 3D environment as a modeling environment significantly changed their understanding of 3D modeling. So let's say they developed a new representation or a new concept of 3D modeling, which involves also their manual or their embodiments. And one quotation is, "When I arrived, I had a good knowledge of 3D programs. Using the cave, we had to totally rethink our concept of 3D. It is a different story, like starting to learn the basics of a new 3D program." The students also reported that they had a rather steep learning process, and they said that at the beginnings they were surprised by the limits of the tools, but then they said, in the course of the study, they found that the limits are very important. And also they discovered that the body is their limit. So making a straight line is not so much determined by the tool, but by their physical ability to make a straight line in 3D space. And the body can both be supporting and constraining. And they also like the sketchiness or the liveliness of the 3D models. And then we asked them about the materiality, in particular, whether they missed it or not. And what we found is that 2 of them did not have problems with the missing materiality. So they said that, basically they said that what they found is a new kind of materiality, or a new way of modeling with something which is not a physical material, but has material properties that you can add and remove and something and do it manually, and that you can develop something which corresponds to what you have in mind. But one student in particular said that he had a problem with the cave in terms of that he could not do what his intention was, so that there was too much noise in the interaction. So that did not allow him to generate an object as he intended it. Yeah. So this is basically the summary of the first TNA.
On slide 20, I guess, you just have one orientation and one position to the tracking system. Why do you need the support by itself? And did you fix the tolerances of your global system? What can be the best calibration for this kind of coding system? Because it could be easy just to take one tracking sensor, within my bus, and we do not need any harm to carry it, and so on. You can just handle it with your hand and you will follow the lines on the surface. Am I wrong?
You're absolutely right. Here you have the possibility to scale the speed or the distance of this stick to the object somehow determines the scale factor. So if you are close to, if you are closer to the object and the axis is longer, then you get a big copy. And if you are, if it's the other way around, then you get a small copy. And you know, I didn't develop this tool. I just describe it. And this is an approach of one of the students up. But you can, of course, also take a pen and try to somehow capture the curvature of an object. This is also possible. When we do something like this, we always get the impression that people start to hold the pen in different angles, so that you do not get such a smooth, straight line, but that the orientation of the stroke changes constantly, so that it doesn't look as nice as it looks here. So I'm rather sure that you could not create an object just by using the pen or just by using the target, and like you see here.
You will need a reconstructed system like marching cube or something like that.
No, we did not use marching cubes here. We have it in our modeling system. We have a virtual clay modeling system, but this is just line-based. There's no marching cube and nothing like this. The next TNA project was called Exploring Opportunities for Immersive Infocom Channels, and this was conducted in last December together with Adam Zappo from the Budapest University of Technology and Economics. So I have to say, it was not my project, and I have to try to explain it as plausible as possible. And I want to start with my understanding of COG-info-com channels. So my understanding is that you have some modalities, sensory modalities, natural modalities like visual, audio, olfactory, various kinds of natural modalities. And you have certain tools, also certain artificial modalities which are able to generate a signal or generate information or data which correspond to the natural modalities. For example, you have a screen which is able to generate visual information which can be graphically perceived or which can be visually perceived. Or you have a speaker which can generate audio which you can hear, and so on. So, and then there is that idea of COG-info-com channels which somehow translates or which somehow defines in a certain language which channel or which modality is mapped to which output or technical, let's say, artificial modality. For example, it defines how the graphic or the visual modality of the user is fed with information, for example, from a screen, or how the hand can use a touch screen, for example. And this defines a certain language, and those language items are patterns or are matches between sensory, artificial and natural modalities. In this project we also used our sketching environment, and here what we did in the project was we developed an over-sketching functionality. So the problem in freehand sketching is that you do not get such straight curves or straight lines as you get on paper. So we wanted to bring this approach to immersive modeling, and we wanted to give the user a certain feedback about the curviness of the 3D curve. And the aim was to support the user during the drawing process, but also during the over-sketching process, and give him an feedback. In this particular case, an acoustic feedback. So what we did was we used our modeling tools and the head tracking tool or the head tracking facilities, and collected the data from the modeling tool from the pen and the C curve, and sent it via the TOEIC framework to the application, and then the application calculated a certain feedback, which was then sent to over the TOEIC frameworks to SuperCollider, which is an audio framework which can just basically generate audio. And the feedback, so you got some feedback about the curviness of the 3D curve. And we also implemented this new functionality over sketching. So our approach was that we had a more direct approach, low-level approach, where we just chose a low-level direct mapping. That means that the line slope variations determine the pitch of the noise you can hear. So this resembles, let's say, the idea of a record, where you also have a curviness of the record, if you want to say so, and this determines the pitch of the sound. And another approach we tried was more a high-level approach, where we had more an iconic representation, so a more complex high-level approach. And here we said the more curvy the line is, the more complex is a harmonic structure you can hear. But here we introduced harmonic structures, not only basic noise, which is one-to-one coupled to the physical layout of the physical form of the curve, but more to the we use high-level concept like harmony or something like this. So the more complex the shape becomes, the more complex becomes the harmonic structure. And now I want to show you a video. What you see here is, it's me, and I draw a very curvy line. Now I start the overdrawing. The sound changes on various dimensions. Another example. So in this example, we mixed the high-level and the low-level approach. So you get a more harmonic or a more complex harmony if the curve is not straight, and you get less complex harmony if the curve is straight. So I think you could hear how the concept changed. So this was a high-level approach. So when the curviness of the line changed below a certain threshold, then also the iconic mapping changed, and so the harmony changed significantly. This was basically the project. We tried to, so what we did not know how the users understand what we give them. Or Adam basically tried to generate sounds which he supposed to were to be understandable for this context, but we had no prior experience about this question, and we tried to do user studies with colleagues of mine, and we manipulated a little bit on the parameters, but we did not conduct a formal study at the end because we were running out of time. But this project is still, let's say, open, and we are planning also a publication of this approach combined with a formal user study. And what we can think of for the future is that we use audio feedback or other kinds of infocom channels, for example, to provide the user with the feedback of the speed of interaction, or the, let's say, the resolution of the resolution of his drawing, or the update rates. So if you the algorithm of the sketching of this sketching system tries to make a best fit between the complexity of the stroke and the time the user takes to detail out something, and we could also give him feedback about this, and about the spatial granularity of his manipulations also. So this could be mapped to something, some acoustic feedback, and then provide the user with it. And we could also make then a formal study if the quality of the interaction changes when if the user perceives such a feedback or not. But this was unfortunately not part of this project. What I can say is that it was a little bit spooky to have such weird sounds in our VR lab all the time, and my colleagues always ask me what we are doing and if this is real work. As you can imagine, having those sounds the entire day in a VR lab is a little bit weird, but it was a really interesting project for me. And what we also learned was that we can use our framework to extend it, for example, to send audio information about it. Yeah, and what we unfortunately did not accomplish is to do a formal user study, but we hope we can do this in the future.
Do you mean that you will be able with this kind of study to go towards a classification of typical sounds which provides specific meanings for people? would it be necessary to get some interactions with other disciplines in order to find the best match between the sounds and the information you want to send? Because clearly now it wasn't clear what was the meaning of a sound when you heard respect to what you expect as noted on the stage. This is the intent, the final intent of the city.
So after the project, I learned that there are well-known patterns, which so there are catalogs of sounds, and which list what connotation a certain sound has. So there's something like sound design, and they already have those catalogs. We didn't have it when we conducted the project, but if we continue, we would take those catalogs and try to apply them to our use case, and then make some variations and do a formal user study to compare which approach is preferred by the potential users. So this was something I learned a couple of weeks after we finished the project in another conference, where I heard someone talking about audio mapping or sound design issues, and yeah, we did not have it available. We tried to do it from scratch, but we haven't. But what I really find interesting is the separation between the direct low-level mapping and the more iconic meaning. So that you say iconic meaning means that you try to transmit some iconic information like harmony or some conceptual thing. And the other mapping, which is more low-level, where you can say, okay, you have a physical structure and you map it one-to-one to a sound, is another approach. But interesting here is that you have both. You have more the direct approach of mapping a physical structure into a sound, or the other approach to say, okay, I have something which is rough, and I map this to a higher complex concept. But we are not very advanced in this. Even though we had 2 weeks time, it took us the technical thing took us very much time, and also this is not the first version of the sound concept, but it's let's say we had 4 or 5 iterations about it.
Another question about the channel you are using. What do you think if you changed sound for vibration, for example? Would you think that it would be more natural having vibration as a feedback to the curviness?
I don't know, because vibration would if you install the vibration in the pen would start to vibrate. So and then you would lose the possibility to make a straight line. So vibration might be, if you want to measure something, then vibration might be a good idea. But if you draw something, you have to do it like this, and when the pen starts to vibrate, then it doesn't help you to make a straight line. The opposite is the case. It would start to make your hand unsteady.
Yeah, so you will compensate the vibration.
Excuse me?
So you will have to compensate the vibrations.
Yeah, right. But you could think of have the vibration somewhere, I don't know, on the feet.
Yeah, on the other hand, for example.
Yeah, on the other hand, something. So these are very interesting fields of research you could open up with this perspective. But it's also a very broad field, and you could think of lots of combinations in this COG-InfoComm channel approach. This project was together with Bela Takarics, also from the Budapest University. And with him, we implemented an immersive collaborative test bed for non-linear control design. And here, and this was a project from the field of airplane design, or from the wing construction domain. And the problem here was that you have, if you are about to design a wing, an aeroelastic wing, then you have to deal with various control variables which determine, which control the wing, and which also determine or give you feedback about the behavior of the wing. And the problem is not well developed yet, or you do not have a full model to simulate such a behavior. And that's why there's still user feedback, or the user is still important in the process, because he has to say whether a certain simulation is meaningful or not. And there are lots of control solutions, and still the user is needed to decide which solution should be chosen or which should be further followed. So the aim of the project was to develop a 3D immersive collaborative testbed which allows to simulate the wing, and also which allowed to observe the control variables. So to give the user, or to give the expert, a feedback about certain control variables. Yeah, and the use cases which I just explained, that the engineer has the task to develop such a wing, and that he develops a certain solution, and he starts the simulation, and what he gets from the simulation is a bunch of data, but he cannot link this data to the actual behavior of the wing. And what we did was that we, as I just said, we developed an immersive visualization for that wing, and we implemented a certain model, and we had we compared 3 solutions which were calculated offline in a pre-process, and we tried to display the control signals in a very intuitive and straightforward manner, and allow the observer, allow the engineer to observe what is the control variables during the simulation process. And yeah, so the possible further directions I will talk later about. So this is the result. So you see here the wing. Unfortunately, I do not have a video. These are just three pictures which I took during the project. So here's a joint, and here's a joint, and you have them here and here and here and here. And if you start the simulation, the wing will rotate like this, and the other part like this. And in this project, we simulated I think it was the starting behavior, so how the wing is moving during the start of the airplane. And on the back, you see 2 control variables. Don't ask me which one. I can look it up at the previous slide. So these are some important control variables for the engineer during the simulation process. And we just did a color mapping, and if those control variables came into a critical into a critical section. So we constantly mapped the control variables to a certain color, which was displayed in the back of the cave. But if they turned into a let's say dangerous or a certain state, then we over-exemplified this by choosing another color, like red in this case. So what happens is you can have a discussion, you can observe your simulation model, and Bela and me, we observed this one and we discussed about it, or he tried to explain the variables to me while looking at the simulation, and he could say, okay, so we could see that if the wing is in a certain spatial configuration, then if the wing is in a certain spatial configuration, then some control variables will change. So you need the background of an engineer to interpret it, but it was very nice to see the real wing moving and having the information from the control variables directly mapped into the same space. This was basically the project, and it took us some time to develop the models and to develop the models on this for this and to connect them with the cave. We did it finally also using our TUI framework. So we developed some sensors, some virtual sensors, which connect to the simulation model and control the position of the spatial of the wing model in the 3D environment. Direction could be that we allow the engineer to control the model on the fly, so that we give him some controllers and that he could say, okay, now I change some parameters of my model and let's see how the system behaves. Then this would require an online simulation environment, which we did not have in this case. We had just offline pre-calculated models. And we could also think of other means of displaying the information other than just colors. Yeah, and also another aspect would be to extend the collaboration aspect and say, okay, if we have all the information distributed using our framework, then we can also connect two caves and show the same simulation on both sides and have a remote discussion about the actual model.
You speak about nonlinear control design. If you change one parameter, the problem is to get the results of a kind of physical simulations in order to know if the new parameter is better than the previous one, if I want understood. So the problem is to be able to provide information in real time with respect to the new parameters in the design. So what was the simulation? Maybe it could be a registered simulation for the tests. But what's the main question?
So the simulation, it was pre-calculated, and Bela has chosen some parameters before. So unfortunately, it was not possible to change those parameters in real time. So we had to, the process was that he did the simulation in an offline tool, generated a text file with the simulation. Then we had an adapter, which was a client in our framework, and this adapter basically sent the simulation data to the application, which in turn changed the position of the wing. So what you could think of is that we implement the modeling environment, or that we integrate the simulation in our framework, and that we control the parameters with interaction devices, something like this. But this was not, we could not realize this in the available time. This was our initial our initial aim, but we did not manage to do this.
What would be interesting anyhow is to get a better vision about how we can process connections to physical simulators and what kind of information you need to exchange. Obviously, it's just a use case, one use case, but we could have the idea within Visionaire to have some way to standardize the connections to physical applications, things like that, in order to have use this kind of information in any case or any other displays. That's quite interesting. Like you made a list of virtual reality system a few weeks before. We have to put that on the website and to clearly identify these elements. But if we want to recreate this environment and this specific environment on another use case, the process should be the same. And the main point is the interoperability with external applications. But we do not, where we do not have a standard solution for that. So it's just a comment.
I said I like the idea, and I said I like the idea, and it's a good comment. And I think if someone else is interested in control design or in the design of nonlinear systems or other simulations, then we could think of defining a common vocabulary on control, on how to control the simulation parameters.